Good day, everyone. Fuels play an important role in the world that we have today. About 359 to 299 million years ago, this was the time of the dinosaurs. This period actually ended. Due to ocean flooding that occurred due to some climatic changes, the vegetation and many species were submerged into the bottom of the ocean. This led to the formation of several layers of thick and spongy materials called the pit. Over millions of years, subsequent deposition of minerals, sand, and clay piled over the thick layers of the pit. This pit had transformed into some forms of sedimentary rock. The increase in the several layers of sedimentary rocks actually increased the pressure upon the pit to squeeze out liquid present in it. Continuous increasing the pressure of the pit had been transforming the pit into what is known today as fuel. So fuels had been transformed from organic matter buried underground after millions of years. Fuels are classified into three types: solid fuels, liquid fuels, and gaseous fuels. The major forms of fuels being used today are coal, petroleum, and the natural gas extract. Fuels are typically combusted in air. We needed air or oxygen for combustion of fuels to proceed. Heat-derived fuels are usually applied for commercial applications. Coal, for instance, is generally a black rock. Coal contains carbon, hydrogen, oxygen, nitrogen, and sulfur. Coal is classified into three main types. We have the anthracite, the lignite, and the bituminous coal. Anthracite is the hardest type of coal. Anthracite has more carbon and it has more energy. Lignite has low carbon content, but it has high hydrogen and oxygen contents. Bituminous coal falls in between the range of anthracite and lignite coals because of its hardness and energy output. In early China, coal was thought to be a stone that could be burned and it could be used for cooking. The Chinese people in the olden times wondered that a stone burns and it is hardly consumed. Later, throughout the world, the use of coal exploded. The coal was used for transportation, used also in factories for the production of products needed by humans, and fuels are also used to power plants to produce electricity. Oil or petroleum is another type of fuel. Oil has been used for 5,000 to 6,000 years. In ancient times, the Babylonians, the Assyrians, and the Sumerians used crude oil already as a fuel source. The crude oil was collected from the Euphrates River. The ancient Egyptians used liquid oil as a medicine to treat wounds and to provide light in some lands. In 1859, Edwin Drake discovered crude oil in Titusville, Pennsylvania. He found out that crude oil was found underground and he tried to pump it out to the surface. He stored crude oil in wood barrels. During these times, Edwin Drake used wood barrels to store crude oil. Wood barrels were known to store wine or some beverages during these times. One of the world's oil supply is derived from the oil wells of California and the Middle East. Crude oil undergoes fractional distillation. Petrol, for instance, contains 5 to 7 carbons in the hydrocarbon chain. Petrol vaporizes at low temperatures and are easily ignited. We call this usually gasoline. Just a single spark, we let it burn at once. It is making it useful for cars, bikes, and smaller engines. Well, these are the cars being used today. It would be better if we would be having this in the future. And I do not like this bike, but maybe this would be better. Kerosene is useful for jet engines and aircraft. Kerosene is also used for rockets. Kerosene is also used for lamps. Diesel is common for vans, trucks, and heavy equipments. Diesel is usually used for bigger engines. Fuel oil from residue is also produced after the production of diesels, usually used for bigger engines also, like found in the ships and power plants. Lubricating oil from residue is also produced after diesel. Natural gas was discovered 2,000 years ago. The natural gas seeds were first discovered in Iran. In the olden times, Iran was called Persia. The ancient Persians discovered the natural gas. They had observed that in the Rocky Mountains, a fire is being produced because of the presence of this gaseous fuel. Natural gas is generally made up of methane. Methane is one carbon and it contains 4 hydrogen atoms. Natural gas has a lower density than air. In other words, natural gas is lighter than air. Natural gas is usually found near petroleum wells, and they are pumped out, purified, and stored. There are 2 classifications of natural gas. We have the dry and the wet natural gas. Dry natural gas contains mostly of methane. On the other hand, Wet natural gas contains other forms of gaseous fuels aside from methane. They may contain ethane, propane, butane, including pentane. Natural gas are actually used for domestic, industrial, and even for power generation. There are other uses of natural gas. Natural gas could also be used fuel as a fuel for vehicles. They also could be used as feedstock for fertilizers and for hydrogen fuel cells. Other forms of natural gas, such as biogas, are used in the countryside for domestic purposes. Let us talk about the combustion process. Combustion process means burning of fuel. For a fuel to be burned, we needed oxygen. Oxygen with the corresponding fuel will be making the combustion process. If we look at the fuel, generally fuel contains carbon, hydrogen, oxygen, including sulfur. If we talk about air, they generally contain oxygen and nitrogen with their proportions according to mole percent. Air contains 21% oxygen, 79% nitrogen. In the burning or combustion process, usually this is done in a furnace or this is the combustion equipment material. Then after burning, a refuse is being formed. Usually, generally, refuse is in the form of ash. Generally, the combustion products are found in the flue gas or the stock gas. The products of combustion may contain carbon dioxide, carbon monoxide, oxygen, nitrogen, sulfur dioxide, and of course, water. There are two types of combustion. We have the complete and the incomplete combustion. There are combustion reactions that we have to consider. Combustion reactions are rapid reactions that produce a flame. Complete combustion takes place when there is a constant and enough or sufficient supply of oxygen. Complete combustion reacts with oxygen with a certain fuel to produce carbon dioxide and water. The equation or the general chemical reaction is fuel reacts with oxygen to produce carbon dioxide and water. So in a complete combustion reaction, the main product will be carbon dioxide and water. If there are other products formed, it is not considered a complete combustion. Incomplete combustion, on the other hand, takes place when there is not enough or the supply of oxygen or air is insufficient. Incomplete combustion reacts insufficient oxygen with a certain fuel to produce carbon monoxide and water. It is also possible that carbon dioxide is still a product. The general chemical reaction is fuel reacts with oxygen to form carbon monoxide and water. For as long as carbon monoxide is present, it is considered an incomplete combustion. Let's consider the burning of propane. For complete combustion, the propane's chemical formula is C3H8. This reacts with oxygen, we needed 5 moles of oxygen, and this produces 3 moles of carbon dioxide and 4 moles of water. If you notice, the chemical reaction is already a balanced reaction. For incomplete combustion, propane reacts with 7 moles of oxygen to produce 2 carbon dioxide, 8 moles of water, and 2 moles of carbon monoxide, including unburned carbon. If there are other products aside from carbon dioxide and water, it is considered an incomplete combustion. For this reaction, we have 2 moles of carbon monoxide and 2 moles of unburned carbon as other products, considering this burning of propane an incomplete combustion. So, as a summary, for complete combustion, if the only products will be carbon dioxide and water, it is complete combustion. If there are other products aside from carbon dioxide and water, let's say carbon monoxide, then it is considered an incomplete combustion. Complete combustion reacts oxygen with a fuel to produce carbon dioxide and water. Let's say, for instance, C8H18. This produces only carbon dioxide and water. It is a complete combustion. Because the air we breathe is only 21% oxygen, a large volume of air is required for complete combustion to take place. Combustion is an exothermic reaction that releases energy in the forms of heat and light. When a fuel undergoes complete combustion, it releases the maximum amount of energy from the fuel being reacted. Complete combustion is usually characterized by a blue flame. Incomplete combustion is also a reaction between oxygen and fuel, but the products are carbon monoxide, water, and carbon. For instance, CH4 reacts with oxygen to produce carbon monoxide, water, and unburned carbon. It is considered an incomplete combustion. Incomplete combustion occurs when a combustion reaction occurs without sufficient supply of oxygen. In other words, the supply of air or oxygen is insufficient to make the combustion complete, therefore making it an incomplete combustion. Incomplete combustion is often undesirable because it releases less energy than complete combustion and produces carbon monoxide, which is a poisonous gas. Incomplete combustion can also produce pure carbon soot, which is messy and can build up in any equipment, for instance, the chimneys that we have. Incomplete combustion is characterized by an orange or yellow colored flame. Although incomplete combustion is undesirable because of its yellowish or orange flame, for centuries, humans have used incomplete combustion of wood to smoke and preserve food such as meat. When wood is burned with limited oxygen, a large amount of smoke is produced, which dehydrates the meat and forms a protective layer or coating that resists bacterial growth. A typical example in the Cordilleras is the meat that is smoked by using wood is called kinuday or kiniing. Gasification is the process of incompletely combusting wood or coal to produce a flammable gas that can be used as a fuel. Until the mid-1900s, many cities produced and distributed town gas, which consisted of carbon monoxide, hydrogen, and methane from the incomplete combustion of coal. This town gas was used for heating, cooking, and lighting until natural gas became commonly available in the 1930s and the 1940s. During the World War II, a shortage of gasoline and diesel fuel led many people and even militaries to convert vehicles to run on wood gas. By 1945, over 1 million vehicles worldwide had been converting to run on wood gas, including over 500,000 in Germany. Chemical reactions associated with combustion process will be the following. We have carbon. Once it reacts with oxygen, produces carbon dioxide, is considered a complete combustion of carbon. Carbon reacting with 1/2 mole of oxygen produces carbon monoxide, considered an incomplete combustion. Hydrogen by itself could also react with oxygen in the combustion process to form water. Sulfur also can react with oxygen to form sulfur dioxide. There are some terms that will be associated with the combustion processes. Let's say ORSAT analysis. ORSAT analysis refers to the type of gas analysis which eliminates water as a component. In other words, it is a dry-free basis. If water is included in the report, it is termed as wet basis analysis. Theoretical air is the amount of air required for the complete combustion of carbon, hydrogen, and sulfur. It does not depend on how much material is actually burned, but what can be burned. Excess air is the amount of oxygen or air in excess or extra or over to what is required for the complete combustion. The percent excess air is also the same as the percent excess of oxygen for the complete combustion to occur. Let's consider this problem. In a given process, 100 kilomoles of carbon is burned in a furnace. It has been found out that 20% of the carbon undergoes incomplete combustion, resulting to carbon monoxide production. The rest of the carbon undergoes complete combustion. Determine the amount of air in kilomoles if 50% excess oxygen must be satisfied. These are some relevant reactions. Carbon reacts with 1/2 mole of oxygen to produce carbon monoxide. First is to calculate the theoretical oxygen needed. We will assume that all of the carbon is burned completely to carbon dioxide. That is for the computation of the theoretical air or theoretical oxygen needed. Carbon burns completely to produce carbon monoxide. This is the main chemical reaction that we will consider to solve for the theoretical air. The theoretical air is solved from the basis of complete combustion of fuel. If we have 100 kilomoles of carbon, we multiply this by 1/1 and we have 100 kilomoles of oxygen. How did we get 1 over 1? It means from the equation, from the chemical reaction, we have 1 mole of carbon will react with to 1 mole of oxygen to produce 1 mole of carbon dioxide. So if we have 100 kilomoles of carbon, it means that the numerator 1 here is actually 1 kilomole of oxygen from the reaction is to 1 kilomole of carbon from the reaction. So kilomoles of carbon will cancel out with the kilomoles of carbon at the denominator here, which is 1. That's why we still get 100 kilomoles of oxygen. For the theoretical air, all we have to do is to convert. If we have 100 kilomoles of oxygen, it means that for 1 kilomole of air, we have 0.21 kilomole of oxygen. And this is always given. It is a ratio that I have discussed, that 21% by mole is oxygen. So the unit now is theoretical air in terms of kilomoles of air. That is why 100 kilomoles will be multiplied by 1 kilomole of air, or for every 1 kilomole of air, we have 0.21 kilomole of oxygen, giving 476.2 kilomoles of air. And that will be the theoretical air needed. The actual air supplied also could be solved. The actual air actually being supplied is the theoretical air that is needed to burn 100 kilomoles of carbon, since the problem says that there is 50% of air in excess, then we multiply 1.5. So the actual air supplied in the combustion process is 714.3 kilomoles of air. It is not correct to do the following. For example, we have here carbon will become carbon dioxide, and then we compute it as 100 kilomoles of carbon, and that will be 0.8, and then we multiply the factor 1:1, and we say that we have 80 kilomoles of oxygen. And then the other one, carbon converted to carbon monoxide, we convert that 100 kilomoles of carbon, and then that will be 0.2 all over times 0.5 all over 1, and then we say that's 10 kilomoles of oxygen. The total oxygen required stoichiometrically based on the actual process is 80 plus 10, and then we have 90 kilomoles. Again, I lectured something that is wrong, and do not do this. We have to follow what we did in the previous slide. Take note, theoretical oxygen is not based on what is stoichiometrically needed according to what is actually burned. The theoretical air is always based from the computation of the complete combustion of a particular fuel. Let's consider again the combustion of propane. Fuels for motor vehicles other than gasoline are being eyed because they generate lower levels of pollutants than gasoline. Compressed propane has been suggested as a source of economic power for vehicles. Suppose that in a test, 20 kilograms of propane is burned with 400 kilograms of air to produce 44 kilograms of carbon dioxide and 12 kilograms of carbon monoxide. Calculate the percent excess air. First is to write the overall combustion reaction for the fuel, assuming it is burned completely. For the reaction, propane reacts with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. For 20 kilograms of propane, the theoretical oxygen required is 20 kilograms of propane. We multiply 1 kilomole of propane is actually 44.09 kilograms of propane. 44.09 is the molecular weight, and we could take it from the periodic table. Carbon will be having 12, and then hydrogen will be having 1 point something. That is why if we take the total molecular weight, it is 44.09. Why did we do that? So that we could convert propane in terms of kilograms into kilomoles. And looking at the chemical reaction, for every 5 kilomoles of oxygen, we have 1 kilomole of propane from the equation. So our final unit here becomes kilomoles of oxygen, because kilomoles of propane cancels out, kilograms of propane cancels out, and the remaining unit will be in kilomoles of oxygen. We now can solve this. We get 2.27 kilomoles of oxygen is the theoretical oxygen to burn 20 kilograms of propane. The actual oxygen supplied is 400 kilograms of air. We will convert air into kilomoles of air. In our discussion, we will consider the molecular weight of air as 29 kilograms per kilomole. I just rounded it off. Actually, it is 28.80 something. So here in our class discussion, we will just round it off to the nearest whole number. The molecular weight of air is 29 kilograms of air is 1 kilomole of air. So that we will convert 400 kilograms of air in terms of kilomoles of air. And converting air into oxygen, we knew it that for every 1 kilomole of air, we have 0.21 kilomole of oxygen. And now we could compute this. It is 2.9 kilomoles of oxygen is the actual oxygen supplied in the combustion process. To solve for the percent excess air or the percent excess oxygen, is the percent excess air is equal to the oxygen supplied minus the theoretical oxygen. We divide it by the theoretical oxygen and multiply it by 100 to make it in percentage. For this example, we were able to solve the oxygen supplied as 2.9 kilomoles. The theoretical oxygen was also solved, and that is 2.27. And take note, we have to divide the theoretical amount of air or oxygen. And we get here 28% excess air. Generation of methane-rich biogas is a way to avoid high waste disposal costs, and burning it can meet up to 60% of the operating costs for such waste-to-energy plants. Consider the complete combustion of 16 kilograms of methane in biogas with 300 kilograms of air. Determine the percent excess air and the total moles and composition of the flue gas. So in the burner or the furnace, we have 16 kilograms of methane being combusted with 300 kilograms of air. The products of the flue gas will be expected to be carbon dioxide, oxygen, nitrogen, including water. Solving for the percent excess air, we have to write the overall combustion reaction for the fuel, assuming that it is burned completely. So methane reacts with 2 moles of oxygen to produce a mole of carbon dioxide and 2 moles of water. For 16 kilograms of methane, the theoretical air required is 16 kilograms of methane. We will multiply the molecular weight. So it means that for every 1 kilomole of methane, we have 16 kilograms of methane. To review, where did we get 16 kilograms of methane? For every 1 kilomole of methane, look at the periodic table, carbon has 12, hydrogen has 1, 1 times 4 is 4, 4 plus 12 makes it 16 kilograms of methane for every 1 mole or 1 kilomole of methane. If we look at the reaction, for every 1 kilomole of methane, it needed 2 kilomoles of oxygen. And we will convert now oxygen in terms of air because what is required is theoretical air. And we knew it, that for every 1 kilomole of air, we have 0.21 kilomoles of oxygen. And for every 1 kilomole of air, it is 29 kilograms of air. So our final unit will be in terms of kilograms of air. And then we get here 276 kilograms of air. The percent excess air is solved by introducing 300 kilograms of air. This is the actual air supplied. And then we subtract now the theoretical air, which is 276 kilograms of air. We divide it by the theoretical amount of air, which is 276, multiply this by 100, and we get 8.7% excess air. To solve the excess air or excess oxygen are actually similar. The value of percent excess oxygen and percent excess air will be the same. With this example, we use excess air. That is why the air supplied was 300 kilograms. The theoretical air which we had solved is 276. From here, we were able to solve 8.7% excess air, or we also can say 8.7% excess oxygen. Isopropyl alcohol is a substance sold as a rubbing alcohol. It is composed of carbon, hydrogen, and oxygen. Combustion of 0.255 grams of isopropyl alcohol produces 0.561 grams of carbon dioxide and 0.306 grams of water. Determine the empirical formula of isopropyl alcohol. If we say empirical formula, this is the simplest formula that could represent isopropyl alcohol, although it is not the actual molecular formula. In the furnace, isopropyl alcohol becomes the fuel, and we burn that with oxygen. The combustion products are given to be 0.561 grams of carbon dioxide and 0.306 grams of water. The mass of carbon in the carbon dioxide is also the mass of carbon that is present in the isopropyl alcohol before combustion. The mass of hydrogen in water is also the mass of hydrogen present in the isopropyl alcohol before combustion. The mass of isopropyl alcohol, which is 0.255 grams, is also equal to the total mass of the carbon in the carbon dioxide, the hydrogen in water, and the oxygen content of the isopropyl alcohol before combustion. To solve for the total grams of carbon, it is given that in the flue gas, we have 0.561 grams of carbon dioxide. We convert grams of carbon dioxide into mole by multiplying or considering the molecular weight of carbon dioxide. So, for every 1 mole of carbon dioxide, we have 44 grams of carbon dioxide. And for every 1 mole of carbon dioxide, we have 1 mole of carbon taken from the equation. And for every 1 mole of carbon, we have 12 grams of carbon. If you notice, our units will cancel out. Grams of carbon dioxide cancels out. Moles of carbon dioxide cancels out. Moles of carbon will be canceling out. Our final unit will be in terms of grams of carbon. And we could solve this, which is 0.153 grams of carbon. To solve for the grams of hydrogen, it is given that the product of combustion in the flue gas is 0.306 grams of water. We will convert water into moles. For every 1 mole of water, we have 18 grams of water. The atomic weight of oxygen is 16 and hydrogen is 1 times 2 is 2. That's why we got 18 grams of water for every 1 mole of water. And looking at the chemical formula of water, for every 1 mole of water, we have actually 2 moles of H. And for every 1 mole of H, we have 1 gram of hydrogen. Or you may use 1.01 or simply 1 only. If you notice, the units will also cancel out. Grams of water cancels. Moles of water will also cancel out. Moles of hydrogen will also cancel out. And our final unit will be in grams of hydrogen. Thereby, we get here 0.0343 grams of hydrogen. To solve for the mass of oxygen, that is actually equivalent to the mass of the sample minus the mass of carbon and the mass of hydrogen. We were able to solve this. The mass of the sample, isopropyl alcohol, is 0.255 minus the grams of carbon in the carbon dioxide minus the grams of hydrogen in water. The final result will give us the mass of oxygen. Knowing the mass of carbon, hydrogen, and oxygen, we can now proceed to solve for the empirical formula. The number of moles of carbon, hydrogen, and oxygen in the sample, let's consider carbon. The moles of carbon is 0.153 grams of carbon, which was solved earlier. We will convert this into mole. For every 1 mole of carbon, we have 12 grams of carbon. Grams carbon will cancel out and we get here 0.0128 mole of carbon. For hydrogen, we were able to solve it as 0.0343 grams of hydrogen. We will convert this into mole. For every 1 mole of hydrogen, we have 1 gram of hydrogen. Grams hydrogen cancels out. Our unit will be in terms of moles or mole of hydrogen, which is 0.0340. For oxygen, we do the same thing. We follow same algorithm. We convert 0.068 gram of oxygen into mole of oxygen. The atomic weight of oxygen is 16 grams. So grams of oxygen will cancel out and our unit will be 0.0043 mole of oxygen. To find the empirical formula, we must compare the relative number of moles of each element in the sample. The relative number of moles of each element is found by dividing each number by the smallest number. The smallest number when it comes to mole, to what we have solved, is 0.0043. This is the number of mole of oxygen. The moles of carbon is 0.0128. We will divide this by the smallest number of moles by oxygen, which is 0.0043, and we get 2.98, and we could round that off to the nearest whole number, which is 3. The next is hydrogen. The moles of hydrogen is 0.0340 moles of hydrogen. We still divide that by the smallest number, which is 0.0043, and we get 7.91, and we could round that off to the nearest whole number, which is 8. For the moles of oxygen, the smallest number is actually 0.0043. If we divide it by 0.0043, will give us exactly 1. So we could say that the ratio of carbon to hydrogen to oxygen is 3 is to 8 is to 1. So therefore, we now can derive and show the empirical formula of isopropyl alcohol, which is actually C3H8O1. Let us consider the combustion of coal. A local utility burns coal having the following composition on a dry basis. Carbon is 83.05%, hydrogen is 4.45%, oxygen is 3.36%, nitrogen is 1.08%, sulfur is 0.7%, and the ash is 7.36%. The average ORSAT analysis of the flue gas during a 24-hour test was carbon dioxide plus sulfur dioxide is 15.4%, carbon monoxide is 0%, oxygen is 4%, and nitrogen is 80.6%. Moisture in the fuel was 3.9%, and the air on the average contained 0.0048 pound mass of water per pound mass of dry air. The refuse showed 14% combined elements as in the coal. This will be for carbon, hydrogen, oxygen, nitrogen, and sulfur, and the remainder being ash. It may be assumed that these combined elements occur in the same proportions as they do in the coal. Estimate the amount of flue gas on a dry basis, the amount of water coming out of the process, and the excess air. Considering the combustion of this coal in the problem, this will be the air supplied in pound moles of air. This will be the analysis of the dry coal used as fuel, and this will be the pound moles of flue gas or the products of combustion on a dry basis. And we also separate now, make it W. This will be the pound moles of water. And the refuse will still contain carbon, hydrogen, oxygen, nitrogen, and sulfur, which is 14%, and then the ash is 86%. With the basis of 100 pound mass of coal, if we make an ash balance, it means the ash that is found in the coal is also the ash that is found in the refuse. So this will be 0.0736 times 100 is equal to 0.86. This is the percentage in the refuse times R, and we were able to solve the refuse is 8.56 pounds or pound mass. The combustible elements in the refuse is 0.14 or 14%. So 14% of 8.56 pound mass of the refuse is 1.2 pound mass of the combustible elements. Assuming the combustible elements occur in the same proportions as they do in the coal, the quantities of the combustibles in R on an ash-free basis are the following. We have CHONS with their corresponding mass, with their corresponding ash-free mass in percent, and their amount in the refuse, and then the amount in the refuse in pound moles. I leave this to you. How are they converted? To find the pound mole and of hydrogen and oxygen due to water in the coal, we multiply 100-pound mass of water and then we multiply this factor. I leave this to you as an assignment. How is the factor taken? The conditions were given previously. And we have here 0.451 pound moles of oxygen. We follow the same procedure or algorithm for the pound mole of oxygen from 100-pound mass. We multiply this factor and then we get 0.225 pound moles of oxygen. To find the mole fraction of hydrogen and oxygen due to moisture in air, we have here 0.0048 pound mass of water for every pound mass of dry air. Review, how did we get this gravimetric factor? And then we get 0.0154 pound moles of hydrogen per pound mole of dry air. Following the same algorithm from 0.0048 pound mass of water per pound mass of dry air. Review, how did we get this gravimetric factor to get 0.0077 pound moles of oxygen for every pound mole of dry air. To solve for A, W, and P using the different balances, if we say balances, it means, for instance, hydrogen balance. If we say hydrogen balance, the amount of hydrogen entering the system is the amount of hydrogen leaving the system. The same thing with other components that we will consider. For example, we will make now the carbon plus sulfur balance. It means the carbon and sulfur that enters the system from, let's say, air and the dry coal is also the carbon plus sulfur that leaves the system, which could be found in R, it could be found in P, but of course it's not found in W because that's purely water. If we make a hydrogen balance, it means the amount of hydrogen that enters the system, our furnace, is also the hydrogen that leaves the system. And we have hydrogen in W because this is water. And we also have hydrogen in P. So we make now that balance and we could make an equation in terms of W. If we make a nitrogen balance, it means the nitrogen that enters the system is equal to the nitrogen that leaves the system. And we make an equation in terms of P. From all of this, we could solve now the values of P, A, and W, which is 44.5, 45.4, and 2.77 respectively. To determine the theoretical air required to burn completely all the carbon, hydrogen, and sulfur in the coal, we do the same algorithm. So you review this. How did we get 6.92 pound moles of oxygen for carbon? And we have 1.11 pound moles of oxygen for the theoretical air of burning hydrogen. And how did we get 0.022 pound moles of oxygen to theoretically burn sulfur? And we add all these three theoretical airs or theoretical oxygen to burn carbon, hydrogen, and sulfur. We add them, we get 8.052 pound moles of oxygen. Since there is already oxygen present in the coal, this amount is deducted or subtracted from the theoretical requirement. The oxygen in coal is 3.36 divided by 16 times 1/2. Review, how was this taken? And we get 0.105 pound moles of oxygen. This 0.105 pound mole of oxygen must be deducted from 8.052, which we previously solved, and we get 7.947 pound moles of oxygen. So the actual oxygen supplied is 45.35. We multiply it by 0.21 to get 9.524 pound moles of oxygen. Our basis is oxygen. That is why we converted the air into oxygen. To solve now the excess air, we calculate this as the actual air supplied, which is 9.524, and then the theoretical oxygen, which is 7.947, divided by the theoretical oxygen. So supplied is 9.524, we had solved that, and then 7.947 is the theoretical oxygen. So we now get excess air as 19.8%. The amount and composition of the flue gas on a dry basis is the amount of water coming out of the process. Well, I leave this to you and you try to solve it. It's your duty to study and solve it. This will also serve as your assignment, and some of these will be asked in the test that soon will be given here. So this is the end of topic 3 regarding fuels. Have a nice day, everyone.